Hello everybody, welcome back. In this video we're going to talk about conditional probability, independence, and the law of total probability. Also, there's something I think you should know. Let's randomly select one card from a deck of 52 playing cards. What is the probability that you get a king? Now, there are 4 kings among the 52 cards, and if we're truly randomly selecting, then they're all equally likely. So the possibility or probability of getting a king is 4 out of 52 or 1 out of 13. Easy enough. Now suppose that someone else, maybe me, got a look at the card and told you that it was a face card. So what that means is that it has a face on it, and there are 12 such cards in the deck. There are 4 jacks, 4 queens, and 4 kings. So I'm going to give you some information that it is a face card, and I'm going to ask you, what is the probability it's a king? And you're going to say 4 out of 12 or 1/3. And that's because you know that you've restricted the possibilities from the total of 52 cards down to only 12 face cards, 4 of which are kings. In this case, where we already know something and have some information, the probability we're computing is known as a conditional probability. The universe of probabilities has shrunk, and if you want to think of it in terms of Venn diagrams and probability as area, we're no longer looking at the entire rectangle. We have shrunk the possibilities down to some subset, and within that subset, we want to know the probability we're in a smaller subset. Now, our notation for generic events A and B is going to be this probability A, then a horizontal line B, and this is read A given B, and this is going to denote the probability that A happens given that we know that B already happened. Let's visualize this with the Venn diagram. Again, the probability that A given B happens tells me I'm already in this set B, and now, once I'm in B, what is the probability that A happens? So given that B is the total universe, the probability that I'm in A is the relative area, the ratio of this intersection probability to the total probability of B. That's the definition of conditional probability. Makes a lot of sense, right? Let's go back to the cards and use our new definition. This may not be exactly how you did it when I told you I had a face card and you computed the probability of it being a king, but let's do it by definition. The probability you get a king, given that you know it's a face card, is, by definition, the probability you get a king and a face card over the probability you get a face card. Now, a king is always a face card, so the probability we get a king and a face card, that event in there is just the event you get a king. It's like in a Venn diagram, we are talking about the probability of an intersection of 2 events, this circle and this inner circle, which really is just the inner circle. So the numerator is the probability we get a king, the denominator is the probability we get a face card. Now going back to the deck, with no information, the probability you get a king is 4 out of 52, and the probability you get a face card is 12 out of 52, which gives you 4 out of 12 or 1/3, which is the same thing we got before when we just kind of thought about it. Suppose that the probability that A given B happens is just the probability that A happens. It kind of seems like it doesn't matter whether or not we know that B happened because it won't change the outcome when determining the probability that A happened. If this happens, if this conditional probability is equal to this probability, then we say that the events A and B are independent events. They don't depend on each other. This is not the usual definition of independence given in statistics textbooks, but this is the one that makes the most sense to me, and I'll get to the usual definition in just a couple of slides. When we're talking about conditional probability, in particular the probability that A happens given that B happens, we have already observed B happening, so it has to be a possible outcome. In other words, the probability that B happens is not going to be 0. There will be some positive probability that B happens. And we need that for this conditional probability to make sense, because it is a ratio with the probability that B happens in the denominator. So when you're working with conditional probability, you usually assume that the probability of the second event after the conditional line is not 0. So in our definition of independence of the events A and B, we have that the probability that A given B happens is equal to the probability that A happens. But on the left side here, let's rewrite this using the definition of conditional probability. It is the probability that A and B happens over the probability that B happens, and it's still equal, by assumption, to the probability that A happens. So if we multiply the probability that B happens over to the other side, we get, if we have independent events A and B, we get the probability that A intersect B happens as the product of the two individual probabilities. This is the definition that's usually given in textbooks. It is fine, but to me, the conditional probability definition of independence, I feel like it's more intuitively clear. You might not agree, and that's okay. So, we now know how to compute probabilities when we're talking about an intersection of independent events. And I have a warning for you, and that is not to confuse independence with disjointness. People do it all the time, and let me give you a couple of examples showing you the difference. So suppose I roll a fair or unfair, it really doesn't matter. Suppose I roll a 6-sided die one time. I'm going to let A be the event that the outcome is a 2. And I'm going to let B be the event that the outcome is a 5. So these events are disjoint, meaning they can't happen at the same time. You can't get a 2 and also get a 5. You only get one of those outcomes. So they're separate, disjoint events. On the other hand, if we roll the die twice, and I let A be the event that I get a 2 on the first roll, and B be the event that I get a 5 on the second roll, these events can both happen. You can roll a 2 and then roll a 5, and if you're rolling completely randomly, then whether or not you roll a 5 on the second roll should not depend on what you got on the first roll. And so these events are independent. So if you want to talk about independent events, you are definitely not talking about disjoint events. They have to both be able to happen. Because for any disjoint event, A and B, the event A intersect B is the empty set, so the probability that A intersect B happens is 0, and that's definitely not going to be the probability that A happens times the probability that B happens, provided these are both possible events. Disjoint, independence, very different. Next up, I'd like to talk about what I like to call unraveling conditional probability. We know that the probability that an event A happens given that B happens is the probability of A intersect B divided by the probability of B. So in this little equation, let's solve for the probability that A intersect B happens. We can write it as the probability that A happens given B happens times the probability that B happens. So this is what I refer to as unraveling the definition of conditional probability. Sometimes what you want is just an intersection probability, not really a conditional probability, but it might be easier to compute in this form. Remember, in a previous video, I said that you want to rewrite probabilities in pieces, and there's lots of ways to do it, and you should do it in a way that takes advantage of the information you have. So the probability that B given A happens is the probability of B intersect A. B intersect A, that's everything that's in B and A both. So that's the exact same thing as the probability of A intersect B, which is how I wrote it here. So starting over, the probability that B given A happens is the probability of A intersect B divided by the probability that A happens, because A and B have switched roles here. So we can unravel this definition, and we can also write the probability that A intersect B happens as the probability of B intersect A times the probability of A. Again, unraveling the conditional probability. In order to compute a probability involving an intersection, if conditional probability is what you know to help you get there to the probability of the intersection. Consider two events, A and B. And suppose I just want the probability that A occurs or happens, which is represented by the shading in this Venn diagram. Note that I can write this as two pieces with respect to B. I can take the part of A that is also in B right here, and the part of A that is not in B. So this first Venn diagram, or this one on the left down here, this is the event A intersect B, and this other one over here is A intersected with B complement. In other words, I can always write an event A as a union of two disjoint pieces with respect to another event. So if I want to compute the probability here, that is the probability of this union, because they're disjoint, Venn diagram, two circles, union is total area, and if you want to compute that, it's just the area of one plus the area of the other. So we've got the probability that A happens can be written as the probability of A intersect B plus the probability of A intersect B complement. And using our new idea of unraveling the definition of conditional probability, I can write the probability that A happens as the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. So for finding the probability that an event A happens by dragging another event B into the problem, this is a technique called conditioning on B, or conditioning on whether or not B happened. Now we were able to write the area for A as the part that intersects B and the part that's outside of B. And note that B, the set B, and the complement of B, they partition the whole space omega. They are non-overlapping pieces, and if you union them together, you get the entire omega. And we can do this a little more generally. So what I have here are sets not represented by circles, but represented by these colored parts in omega. And I happen to have 11 sets here represented by these colors, and I have the set A sitting where it's always been sitting. So this is a more drastic partition of the sample space omega. In other words, I have many sets. In general, I'm going to call them B1, B2 out through Bn in this picture, n is 11. And in order to create what is called a partition of omega, they need to be disjoint, and they need to fill up all of omega, which means if you union them together, you will get omega back, and you're not missing any parts. When we wrote the probability for A, conditioning on whether or not B happened, we took advantage of the fact that A can be written as an intersection with a bunch of disjoint pieces, and we added them together. So in this picture, I can look at the probability, I can look at the area that's in the A circle and also in this dark blue region, and I can add on the area that's in the A circle and also in this gray region, and I can add on the area that's in the A circle and in this kind of bright orange region, and finally use this red or dark orange region down here. But I can also add on the probability that A intersecting the green region happens because that intersection is empty, and the probability of an empty set is 0, so throwing on some extra zeros when calculating the probability that A happens is not going to hurt anything. So let's try it. The probability that A happens can be written as a sum of probabilities because A can be written as a union of disjoint sets. So I'm going to take the part of A that intersects with B1 and the part of A that intersects with B2 out through, in my picture, the part of A that intersects with B11. And because they're disjoint, I get to sum these. And this is just notation for that sum. It's a little more compact formula, so this capital sigma is summation notation. And this says you put in I equals 1 through n and add them all up. And now I'm going to unravel the definition of conditional probability in order to write this intersection probability as a conditional probability times what is known as a marginal probability. On this slide, if you take this first guy up here and go to the end, the punchline is known as the law of total probability. So if you want to find the probability that an event occurs, you can drag in every other possible event as long as they're disjoint and make up the whole space. In the next video, we're going to see examples using the law of total probability and other concepts that we talked about in this video, and we're also going to talk about Bayes' rule, because sometimes things just seem backwards. I'll see you in the next one.